in understanding the gravitational field in scalar terms. That is, now we shall be talking about the gravitational potential energy and gravitational potential. Gravitational potential is defined as the work done by the force of attraction in bringing a unit mass body from infinity to that point of interest. That is, if we are to find the gravitational potential because of this mass at a distance r, so for that what we do is, that is, we have a one body, let's say 1 kg mass, unit mass body at a distance infinity from here to here. We just give a gentle push, or we hold it and bring it over here gradually, and so whatsoever is the work which is done by this force of attraction from here, from infinity to at a distance r, that is point A to point B, so whatsoever work is done per unit mass, that is known as the gravitational potential because of this at this point, that is at a distance r. If this is mass m, we can also find what is the work which is going to be done by this force of attraction in bringing it from infinity to this point. Let's find out. So for that what we do is, we take any general distance x from center to center. This is a point mass body, let's say its dimensions, they are almost equal to 0, and this is the other body which has a mass m. The distance between their centers at a particular moment is, let's say, x. So now the force of attraction between the two is going to be gmm upon x square. We are interested in finding the work done by this force of attraction when this body is taken from infinity to this point at a distance r from its center. So we know that is work is f dot dx, scalar product of force and displacement. We also understand that is x is variable in this case, x is changing, so it means this force is variable force. If this is a variable force, so certainly we shall be making use the methods of calculus, that is integration. So as usual, what we do is, we find what is the total work done in moving this body by a small distance dx. Now thing to understand is the force is also in this direction, gm upon x square, that is in this direction, and displacement is also in this direction. So when we say f dx cos theta between force and displacement, the angle is 0, theta is 0, so this cos 0 is 1, so it comes out to be f dx only. So the small work done is going to be f dot dx. So the total work done is going to be integral of dw is going to be integral of f into dx. And the limits, we have to take infinity to at a distance r. Infinity is the initial distance and r is the final distance between the two. So this comes out to be f is g m m upon x square dx infinity to distance r, and we can do it over here. So this comes out to be g m m is constant, so this comes out to be x raised to minus 2 dx infinity to r. So this comes out to be gmm, increase the power by 1, that is x minus 2 plus 1, and increased power comes in the denominator. Limits, they are infinity to r. So this comes out to be gmm minus 1 by x, this is x raised to minus 1, and this is minus 1 infinity to r. So this comes out to be minus, we can take out gmm 1 by x infinity to r. So this comes out to be minus gmm 1 by r, upper limit first, minus, then we put the lower limit in this expression 1 by infinity, so it comes out to be minus gmm upon r. So this is what you say is gravitational potential energy. We have taken this mass as m, so it is the gravitational potential energy, that is interaction energy between these two. When the body has come from here to here at a distance r, it has come, so this is the interaction energy at this moment, that is gravitational potential energy between the two. If we have to find the gravitational potential, then certainly we take this as mass m as 1 kg, so this comes out to be minus gm upon r. So the gravitational potential because of this over here at a distance r is the work done in bringing a body of not mass m kg but unit mass body from here to here. It means m is equal to 1, we put m is equal to 1 over here, so it comes out to be minus gm upon r. This comes out to be negative, this comes out to be negative. What does it mean? It primarily means that is when the bodies, they are at an infinite distance, there is no interaction between the two. There is no force of attraction, there is no force of repulsion, so there is no question arises of any dispute, be it of attraction or be it of repulsion. There is no interaction. When there is no interaction, then certainly there is no potential energy. Potential energy over here, what we're talking about, it is because of field. In case of springs, like this, which has a spring constant K, we had done earlier in Newton's laws of motion also, that is the potential energy comes out to be half kx square. This is the potential energy because of the configuration. Over here we are talking the field energy, and this field, gravitational field, or be it electric field or be it magnetic field, they are conservative fields. It means if we have to take any mass from here to this point to this point, the work done is going to be same, whether you go by this path or you go by this path or you go by this path, any path you take, the total work done from point A to point B is going to be independent of path. That is the basic definition of conservative field. So now when these two bodies, let's say this M and this M, they are at an infinite distance apart. So it means the gravitational potential is, suppose denoted by U, is equal to 0 and kinetic energy is also equal to 0. Suppose this body is stationary, then kinetic energy is also equal to 0. So the total energy, total mechanical energy is also going to be equal to 0. And now at this point B, if we consider point B, what is the potential energy? Gravitational potential, we are saying it is minus gm upon r. Initially it was 0, now it is minus, it means there is loss of energy. So what is the loss of potential energy? So when we take the first situation, when this mass capital M and small mass m, they are at a distance, infinite distance apart, so the force between the two is going to be gmm upon infinity or infinity square, one and same thing, that is going to be equal to 0. So as a result, the gravitational potential energy between the two is going to be equal to 0, and at this moment we take kinetic energy is also equal to 0. So this is for first case. We are also assuming that this body is not moving, this is fixed. Otherwise, if we release both the bodies in space, so this will move this way and this will also move this way. So right now we are not considering its motion, though if released in space, these two bodies, they'll start moving towards each other and the center of mass will remain stationary. But right now we take this body as stationary and this only as moving this way. So when the distance between the two is infinite, the gravitational potential is 0 and kinetic energy is also equal to 0. Now if it is slightly given a very gentle push, so as a result, now it starts moving in this direction, and gradually, because now there is going to be force of attraction between the two, this is going to attract it. As a result, this will gain some kinetic energy. So when this body reaches at a distance r, this body of mass m is going to have velocity v also. So now what is the gravitational potential energy? For 2 it is minus gmm upon r, and what is the kinetic energy? Kinetic energy is going to be half mv square. The point to note is no external force has done any work. So that's why we can use the conservation of mechanical energy principle. So whatever is the initial total mechanical energy when they were infinite distance apart, the same total mechanical energy is going to be possessed by the system at this time also. So initially we say that is equal to 0 plus 0, that is total mechanical energy of this system is 0. Of this we say it is minus gmm upon r plus half mv square, or gmm upon r is going to equal to half mv square. So now if we know the principle of conservation of mechanical energy, we know that there are no dissipative forces. As a result, the loss of potential energy should be exhibited in the form of gain of kinetic energy. That's the same thing what is happening over here. Over here potential energy is 0, over here the gravitational potential of the system is minus gm upon r. So loss is what? Loss in terms of, this is the gravitational potential energy. So loss is 0 minus gm upon r, that is gm upon r, this is a loss of potential energy. So this loss of potential energy should exhibit itself as gain of kinetic energy, that is half mv square. So we understand gravitational field in two ways. One is vector methods, the other is scalar methods. In vector methods, we understand the gravitational field strength. The gravitational field strength or gravitational field intensity of a body of mass capital M at a distance r is the force experienced per unit mass at that point which is situated at a distance r from the body of capital mass M. The gravitational potential is the work done by this force of attraction in bringing a body of unit mass from infinity to that point, and it is minus gm upon r. Because of this over here, it is gravitational potential is minus gm upon r. Gravitational potential energy is minus gm upon r. It is the work done in bringing a body of mass m from infinity to this point at a distance r from this body. So this is the gravitational potential energy. Now if we have a number of masses, let's say we have m1 mass over here, m2 mass over here, and m3 mass over here, and we have to find the net gravitational field strength over here. So what we do is, let's say this distance is r1, this distance is r2, this distance is r3. So because of this, the gravitational field strength is in this direction, that is gm1 by r1 square. Because of this, at this point P, it is gm2 upon r2 square, and because of this, it is going to be gm3 upon r3 square. So now there are three vectors, and we can find the net gravitational field strength at the point P. But if we have to find what is the gravitational potential over here, we don't have to deal with the vectors. We can algebraically add all the gravitational potentials because of three masses at this point P. That is, if this is m1, distance is r1, over here it is m2, distance is r2, and over here if it is m3 and distance is r3, at point P, that is gravitational potential at point P is going to be, because of this over here, minus gm upon r1, plus because of this minus gm upon r2, and because of this over here plus minus gm upon r3. We can add the three and we can find the total gravitational potential because of this mass configuration at the point P. Now if we talk about the gravitational potential energy of the system, let's say we have two bodies. One is of mass m1 and the other has mass m2 separated by distance r. So the gravitational potential energy of this system is going to be minus gm1 m2 upon r. If we have around say three bodies, let's say this is m1, over here m2, and over here we have m3. They are like this. This is at a distance r1, this is at a distance r2, and the distance between these two, m2 and m3, is r3. Then the gravitational potential of this system is, first let's take the gravitational energy of this and this system. That is minus gm1 m3 upon r2. This is done. Now this and this, they are also interacting. So their gravitational potential energy is plus minus gm2 m3 upon the distance between the two, r3. This is interaction is done. Now interaction between these two. So it is going to be plus minus g m1 m2 upon r1. You add this, all these, you will find the gravitational potential energy of the whole system. So once we understand the gravitational field, the next topic we shall now be going to is Kepler's laws of planetary motion.